Cool. So tonight we're going to have a little bit more another look at transformers. Specifically, we'll be looking at instrument transformers to start with, and then after that, looking at efficiency. Cool. So instrument transformers. So there are two types of instrument transformers, and they are potential transformers or PTs and current transformers or CTs. We did touch on this last week. I think I did glaze over it a bit. So instrument transformers, they're specifically designed so that regardless of the voltage being applied, current flow through either the primary or secondary windings is kept to a minimum. This is accomplished by designing the windings with precision, so the relationship between resistance and reactance is finely tuned. So you guys would have looked at reactance back in AC theory, and that being both inductive and capacitive resistance, which obviously affects the actual power measured. You can also, in series, in parallel, affect current flow. Cool. So potential transformers. So the purpose of these, a potential transformer, it's essentially a double wound transformer. It's connected to high voltage lines across the primary windings so that a low, more measurable voltage is induced into the secondary winding for the purpose of instrumentation. So the concept, the winding turns are proportional to voltage, so we can accurately measure the voltage of a high voltage supply without needing instruments that can handle such voltages. A voltage transformer is often connected to a measuring device that automatically calculates the high voltage value by multiplying the low voltage value by the turns ratio. We looked at the turns ratio. The number of primary turns over the number of secondary turns is equal to the voltage primary over the voltage secondary. That's why they're also known as voltage transformers or VTs. So you'll hear CTs, PTs, and CTs thrown around if you're ever talking about measuring high voltage, or high current. But due to the fact that we're learning about all manner of voltage converting transformers, we'll differentiate the two by calling the instrumentation type of a transformer PT. So the construction, so it's built much the same as a double wound transformer. There are two windings placed upon a ferromagnetic core made out of laminated silicon steel plates. So the main difference between a PT and a standard double wound transformer, the PTs are designed to keep primary and secondary voltage currents to a minimum, so that there is very little change in voltage when current is drawn. In other words, volt drop is kept to a minimum to keep the readings as accurate as possible. The secondary voltage of a PT generally never exceeds 110 volt, even when the primary voltage can differ greatly. They come in three types. So conventional wire wound or electromagnetic type. The circuit diagram here is a representation of that. Capacitive type and optical type. So a conventional wire wound type are just, as you would imagine, basic double wound transformer. These types are used with relatively low voltage ranges. Capacitive type PTs utilize a chain of capacitors between the high voltage terminals and the windings in order to further isolate the electrical circuit. Optical type PTs use what is called the Faraday effect, where the relationship between light frequencies and voltage fields determine the level of voltage. This type is used for greater electrical isolation and when elimination of factors such as phase displacement across windings is required. The three-phase PTs are essentially three single-phase PTs in star configuration, so specifically in star configuration. So we'll look at how these are connected along with CTs in order to create a full energy consumption meter shortly. Now, the reason it's connected in star is because that gives us our neutral point. So going back to transformer basics, star delta. So in delta, we have no neutral. So we get 400 volts no matter where we measure. But obviously in star, we get 230 and 400 because we have that neutral point. So current transformers. So current transformers or CTs are used in installations that draw large quantities of current. So that's where, like your high-rise buildings, so you'll have your main meter or your incoming meter, which is used to calculate communal power minus tenant power. You'll have big CTs around the big cables to measure the overall current coming into the building. And then that can be, you can have the individual tenants use subtracted from that. And then you figure out the common power or the communal area power. And then that is divvied up among tenants. So they're used in installations that draw large quantities of current. Typically, a revenue meter can handle anything up to 100 amps per phase. So that's your standard revenue meter that you have in your house. Has anyone here hung, rehung, taken off, or played with a current revenue meter? Yeah, to be fair, it's not usually something that you'd be doing in second year. But, you know, on the off chance that you guys have assisted your tradesmen with one. One thing to remember, as my colleague pointed out to me earlier while we're having discussion, if you're taking a meter off for any reason, like to do a board upgrade, make sure it's unpowered first before you open it up, because if it's powered when you open it up, it sends a signal to the metering company that it's been opened. And it costs about $180 to get the meter resealed. And it's probably the same person who's coming to do your inspection, especially if you use Telfa Electrical anywhere in the Pororua, Wellington area. Cool. So yeah, installations that draw more than 100 amps per phase will often employ CTs to represent the installation's current draw, but reduce the value to that which the meter is capable of measuring, and these are called CTs. So CTs can also be employed to protect high current circuits by reducing the incoming current value to a level that can trigger a device that opens a large set of contacts to interrupt the main supply. These are called protection CTs. We will discuss the difference in construction and operation between these two types shortly. No matter their application, all CTs are designed to reduce current proportionally to the incoming supply. You'll also see current transformers and CTs on solar installations. This is to track current traveling back and forth along the meter and to ensure that you're getting accurate payback from when you export solar. Cool. So construction. So CTs can also be referred to as series transformers, as the primary side of the transformer is typically in series with the load being measured. This means that the primary turn is made of very few turns. In fact, some may only consist of the flat conductor passing through the core. Others may have one or two turns around the core. The secondary winding then usually consists of many turns on a laminated core of low-loss materials such as silicon steel. The core is of a large cross-sectional area so that a low flux density is created using smaller wire. Cool. So there are three types of construction methods for current transformers. You've got your bar type. The CT uses the buzz bar or conductor as the primary winding and is bolted in series with it. They are capable of measuring currents over 200 amps, and due to their solid construction and oil and porcelain insulation, they can be used on the highest of transmission voltages. That's your bar type there that's showing now. So wound type, that's this one. This CT also uses the buzz bar or conductor as the primary winding. However, when bolted in place, the conductor then turns around a core a certain number of times. The secondary current is determined by the number of turns the primary makes. And then the last one is toroidal core. This CT does not contain a primary winding. Instead, the CT is placed around the conductor being measured, and the conductor acts as the primary winding without being cut into. Some toroidal type CTs have a split core, which allows for the core to be opened and removed from the conductor without having to do any electrical disconnections. So the last one there, the toroidal type CT, is the most common one you'll see. It's also sometimes referred to as a jaw type because it can open and then close. And these are most commonly used for revenue metering in large commercial environments like an office building and schools, and also solar installs for your home. Cool. So operation. So CTs are constructed so that the secondary winding will deliver a proportional amount of current in regards to the primary with a high degree of accuracy. These secondary currents often classify the rating of the CT depending on the application. A typical CT will deliver either 5 amps or 1 amps maximum on the secondary. This value is combined with the primary current to give a ratio. For instance, a typical CT is a 300 to 5. So let's look closer. A 300 to 5 ratio means that when 300 amps flow in the primary, 5 amps will flow in the secondary. The meter or instrument is programmed to realize that there is a CT being used with a ratio of 300 to 5. So when it sees 5 amps flowing through it, it reports 300 amps. If it detects 2.5 amps, then it knows that 150 amps will be flowing in the primary. Modern CTs tend to have a secondary rating of 1 amp. So a 500 to 1 ratio means that for every 1 amp flowing in the secondary, 500 amps is flowing in the primary. See there, you've got the 301 CT wrapped around your primary, and you've got a test block, and then you've got your ammeter or revenue meter. So you don't need to connect around the neutral. You only need to connect around the phase, because your alternating current and the way it's wrapped around the conductor will create a positive phase and neutral on the other side of the transformer because of the alternating current. Cool. So hazards and safety. So CTs can be dangerous when worked on by anyone who does not know how they function properly. So if you come across one, don't work on it unless you have someone who's trained in them, because you may accidentally discharge it into you. So it's important to know how they operate so we can understand the dangers they pose and how to work on them safely. So because the CT has very few turns on the primary side, its reactance is very low. This means that the primary current remains very much unaffected by the magnetic effects of the CT. Conversely, the secondary is made up of a lot of turns, so has a relatively high reactance. When the secondary side is fully loaded, these turns provide enough demagnetizing force to counteract the primary, which limits the voltage applied to the secondary winding. If, however, the secondary is open-circuited while the primary is still energized, the pushback that the secondary was providing is lost. The results are this. The magnetizing current within the core exponentially increases, which can damage the core badly. The core loses its ability to be magnetized the same way it was before, effectively rendering it useless. The flux density of the core increases as well. This induces a very high voltage across the secondary terminals. This voltage can damage insulation and become a serious shock and fire hazard. So, yeah, they're great tools, but they have a lot of drawbacks in terms of if they're not looked after properly or anything goes wrong, there's a high chance of damage, fire, and possible electrocution. Cool. So to this end, CTs must never be open-circuited while energized. If they require work to be done on them or replaced, the secondary side must be short-circuited so that the current will still flow before removing the connection. Most metering setups come with what is called a test block, which we saw before, which is a set of terminals with hinged connections that the CTs are terminated into. So when they are to be worked on, they can easily be shorted out before they are disconnected. Fuses must never be used in the secondary circuit of a CT also. This is because if there is a surge in current in the primary, it will be reflected in the secondary, which could cause the fuse to operate. If they operate, they essentially open circuit the CT, creating the hazards we talked about before. So you'll never find a fuse on a CT leg. If someone says that you need to install one, please refer them to how dangerous it would be if that fuse were to blow. Even if it was like a 50 amp fuse, it's still not worth the chance that it might blow and then cause the dangers we were talking about.
Hey, Santino, could you go get me a CT from the workroom?
Yeah, sure. Do you want a big one or a little one?
Well, we have to monitor the main breaker current in the switchboard, and it has to be highly accurate for metering and protection and go around 4 different 500 MCF cables.
So a big one, as long as it fits around the wires, it'll work, right?
Well, sometimes that's true, and there's actually a lot of different things to know about CTs because you have different ratings, different classes, different high frequency ones for measuring different transients.
I didn't know that. Now, I know you've been working on some new demos with CTs. Hey, is there anything else you could tell me about current transformers?
Yeah. First, let's back up a little bit and define what a CT or current transformer is. A CT is a current measuring device that is used to safely reproduce a low-level current that accurately represents a higher current level for the purpose of metering and protection. Let's start with a simple explanation that describes the most common ways of calculating and measuring current using current transformers. By applying Maxwell's equations, specifically Ampere's law, we can say that if a magnetic field is integrated around a closed loop of wire, the value of that integral is equal to the net current enclosed by the loop. CTs are closed loop instruments consisting of a magnetic core and a secondary winding around the core. The primary winding of the CT, the main loop, has the wire with the current we wish to measure pass through the center of the core. The primary winding that carries the main current is said to have a single loop or winding. The wire produces the magnetic field that drives the current on the secondary winding, which is used as the output of the CT. The current on the secondary winding is proportional to the current flowing through the center of the core. Typically, the secondary rating is 5 amps or 1 amp. For example, with a 1005 rating or a turns ratio of 200 to 1, when 1000 amps flows on the primary circuit, 5 amps would flow on the secondary winding. Current transformers are primarily used for metering and protection applications and come in various sizes, shapes, and ratings. CTs can be solid core, split core, or clamp-on styles for both low voltage and medium voltage applications. Solid core CTs are generally more permanent, are most commonly found for metering and protection in switchboards, panel boards, and switchgear. Split core and clamp-on CTs are generally used in more temporary applications, such as power quality instrumentation. For permanent applications like protection and metering, CTs can be found anywhere from generators to transformers to connected loads, or anywhere we want to monitor current flowing in the system. For example, utilities use CTs at their customers' incoming service to monitor the current and power usage for billing purposes. These CTs must be extremely accurate and are considered revenue grade since they are used for billing. Permanent CTs are also used to monitor power and power factor so that real and reactive power can be optimized. On the protection side, CTs can be used in combination with trip units for low voltage circuit breakers and relays for medium voltage breakers to trip the breaker when there are overloads or faults on the system. Many circuit breakers have built-in CTs used to monitor current. As a point of clarification, a lot of people call CTs sensors when they are mounted inside switchgear or circuit breakers. But the functionality and purpose is the same, to get current measurements to a useful level. A single CT is generally needed for each phase and neutral to monitor current, but for ground fault protection, a special type of CT is used. All of the phases and neutral conductors go through the ground fault CT, and if any residual current exists, in other words, current comes in on one of the phases but doesn't return on the other phases or neutral, then there is a ground fault. In your house, this is triggered by a 5 milliamp level, and industrial plants, this may be 30 milliamps or even a couple hundred amps. Ground fault protection is generally for personnel safety in homes and equipment protection in industrial applications. In medium
Those
voltage
measurements obviously don't apply to New Zealand because we use 30 milliamps for residential.
Needs to be rated for the line voltage that the CT is measuring. For example, 13.8 kV. However, this is not the case because the CT is installed around an already insulated and typically shielded conductor. Most CTs in secondary winding insulation is rated at 600 volts. In medium voltage switchgear, the CTs are physically mounted around an insulating material or use physical separation to insulate the CT from the energized bus with an air gap. For all protection applications, CTs must be rated to accurately measure the high currents that are possible during fault conditions, usually 20 times full load amps, so that the breakers can trip in the proper sequence without saturating, which yields an incorrect result. CTs come in many different ratios, such as 100 to 5, 300 to 5, 5,000 to 5, 60 to 1, and some have multiple taps where the ratio can be selected in the field or for a specific application. Let's take, for example, 300 to 5 amps, meaning that a wire carrying 300 amps AC flowing through the core will produce 5 amps on the secondary winding. Most CTs have a 5 amp output, but others have 1 amp. So when interfacing with a meter or circuit breaker, the correct multiplier must be used that will convert the 5 amp or 1 amp to the actual measured value. But even though the current steps down 300 amps to 5 amps, the voltage will step up on the secondary winding. An open circuit on the CT secondary winding can have dangerously high voltage of thousands of volts. When CTs aren't used, they should always have their secondary winding shorted for safety by using a shorting block or a temporary jumper. All CTs output a current that is then used for metering, but temporary CTs, like those used in Fluke and other power quality instruments, add a terminating resistor on the secondary winding so that they output a voltage and can be open circuited when connecting the meter. With this resistor, these CTs typically have a rating of 10 millivolts per amp or 100 millivolts per amp. The lower range ratio is usually used for secondary measurements, in other words, clamping onto the 5 amp secondary of another CT. Sometimes the current value is too small. A CT may not be accurate at less than 10% of its full load rating, so one way to increase the amount of current flowing through the core, especially for temporary metering, is to loop the primary wire several times through the core. For example, for a 500 to 5 amp CT or a 100-to-1 ratio, looping the wire 5 times through the core will make the CT ratio 100 to 5 amps. So if 20 amps of current is flowing on the primary circuit instead of 0.2 amps, 1 amp of current will flow on the secondary, making the measurement more accurate. CTs come in a variety of accuracy classes. For example, the ratio of primary to secondary current error of a class 1 CT is 1% rated current. A 0.5 rated CT is 0.5% or less. The accuracy of these devices is very important for protective relaying and metering. They have specific requirements for overload currents in excess of the normal rating to ensure accurate performance of the relays during system faults. A current transformer can have a range of ratings from C10 to C800, which is related to the secondary winding output voltage capabilities and VA rating of the CT. In simple terms, this means that a CT with a higher rating can sustain more burden on the secondary without saturating. For example,
Okay, that's probably a bit more detail than we really need to go into. You can really start getting into the weeds with all this kind of transformer metering stuff. But so far, all we need to know is that the basics of how CT works and how it takes a high current and turns it into a low current by using mutual induction and the transformer winding ratios. Of course, all equipment, no matter how big or small, consumes some degree of energy for them to work. So instrument transformers are no exception. There is always a degree of load in a circuit, whether it be measuring equipment or the wiring itself. The load that is connected to the secondary side of an instrument transformer is called the burden. The burden is measured in volt amps and typically used to represent this as the unit VA. So to calculate burden, so the power used by the secondary circuit is dependent on the impedance, impedance being the AC version of resistance, and the current flowing through it. So we've used the formula to calculate its power consumption before. P burden equals I squared times Z, the impedance. Instrument transformers often come with a VA rating, which states the maximum burden that can be placed in the circuit. When operating that instrument, if this rating is exceeded, then the instrument will not read accurately. It is advised to keep the burden of the circuit as low as possible. However, we are governed by the length of the run and the size of the cable we wish to use. In this case, we can calculate the rating of the instrument transformer using the following method. First, we must know the total impedance of the circuit we are going to be connecting the instrument to. This is as simple as adding together the impedances of the wiring and the instruments. So Kirchhoff's law, or resistances in series add up together. The total resistance of a series circuit is the sum of the resistances. So let's say the leads connected to a CT, connecting the CT to the ammeter have an impedance of 0.2 ohms each, and the ammeter has an impedance of 0.1 ohm. So ZT equals Z1 plus Z2 plus Z3, which gives us 0.2 plus 0.2 plus 0.1, which gives us the total impedance of 0.5 ohms. So the next step is to substitute that value into the formula with the maximum current value the instrument is expected to produce. So for example, 305 CT will produce 5 amps in the secondary when the primary load is 300 amps. So we use this figure, I squared times Z, so 5 squared times 0.5 gives us 12.5 VA. The burden of this CT is 12.5 VA. A typical rating for a CT is 15 VA. So this would be suitable. So here we have a typical metering setup. So this diagram shows a possible setup for a large high voltage installation with all metering possibilities. This is the case. This is not the case for every installation. So low voltage installations may not require VTs. However, whenever CTs are used, the meter must also have a mains connection so that a voltage reference can be used. Bear in mind that the orange is not recognized conventional phase color. It is used in this diagram to show white phase. See there, you've got the revenue meter control equipment. So you've got the primary side of L1, 2, and 3 connected to 3 different double wound transformers with an inline fuse, which are then connected to the neutral conductor. If there was no neutral conductor, you would simply connect all 3 tails, secondary sides of the primary coils, primary windings, there we go, together to create a star transformer setup. And then you've got all 3 of the other side connected to V1, V2, V3, V reference, and an earth point. So that's basically a earth neutral point or a ground reference point. And then you've got your control equipment, which are CTs. They're all connected around the coil, so they do not need a neutral. However, the secondary side of all of them are connected to each other to form a star or neutral point, and then that is then earthed as well. Cool. Yeah, this do not perform any illegal activity or criticisms. This is all content provided by the channel to educate only.
Current transformers and potential transformers are devices that allow us to measure large currents and voltages without causing damages to the measuring device. The main difference between current transformer and potential transformer is that the current transformers uses a step-up transformer in order to reduce current through its secondary coils, whereas the potential transformers use a step-down transformer in order to reduce the potential difference across its secondary coil. In this video, we will go to learn the difference between current transformer and potential transformer. The secondary of a current transformer cannot be open-circuited on a circumstance when it is under service. The secondary of a potential transformer can be open-circuited without any damage being caused either to the operator or the transformer. A current transformer may be considered as a series transformer. Potential transformer may be considered as a parallel transformer. The primary current in a current transformer is independent of the secondary circuit conditions. The primary current of a potential transformer depends upon the secondary circuit conditions. The primary winding of the current transformer is connected in series with the line carrying the current to be measured. Hence, it carries the full line current. The primary winding potential transformer is connected across the line of voltage to be measured. Hence, the full line voltage is impressed across its terminal. With the help of a current transformer, a 5 ampere ammeter can be used to measure a high current like 200 ampere. With the help of a potential transformer, a 120 voltage voltmeter can be used to measure very high voltages like 11 kilovolt. Dear sir, thanks for watching the video.
Cool. So yeah, current transformer, potential transformer. They basically work on the principles that would be most beneficial. So a current transformer is in series because in series current never changes, and a voltage or potential transformer is in parallel because in parallel all voltages remain constant. Although it is a transformer, so it is a step down or step up. Cool. So now we've had a look at current transformers, we're going to take a look at, or another look at transformer efficiency, so regulation and safety and legislation. So transformers, so we need to be aware of transformer losses because they're not 100% efficient. So there's always losses when energy is converted from one form to another. We strive to minimize losses as much as possible so the equipment we're using can deliver an output power as close as possible to the input power. However, this cannot be perfectly attained. So just remember, it's always lost. It's never destroyed. Energy can never be destroyed. It can only ever be converted. So we convert voltage to voltage, but because there's losses due to heat and inefficiencies, we do have losses, but it's never, it doesn't go nowhere. It goes somewhere. So because transformers have no moving parts, there's far less wasted energy compared to something like a motor. However, because there's current flow through a conductive material and this current is rapidly changing direction with AC, there are some losses. So there are two main types of losses we attribute to transformers. So iron losses and copper losses. So when we talk about iron losses, we're talking about the losses due to the electromagnetic induction in the core. So it does not matter what load is connected to the secondary winding, the losses will always be the same. Even when no load is connected at all, it requires energy to maintain the iron, magnetize the iron core. Even if the core is not inducing anything into the secondary winding, because of this, we call these losses constant or fixed. The value of them are always the same, no matter the load. So these two types of iron losses, eddy currents, and what we call hysteresis. So when we talk about eddy currents, so these are currents that are induced into the core. So as we know, any current flow in a conductor creates heat due to the resistance of the conductor. Transformers are no different. Current constantly circulates through the core when it's magnetized and is considered a loss or wasted energy because it is not useful to us. We can minimize these eddy currents by building the core of a more resistive material, such as silicon steel. This alloy is still very good magnetically speaking, but has a higher resistance, therefore lowering the amount of current flow within it. We can also limit these eddy currents by reducing the cross-sectional area of the core. We still need a good amount of steel to achieve maximum electromagnetic induction. However, if we build this core out of thin laminations that are insulated from each other, we have effectively created the same size core, but reduced the cross-sectional area in which current can flow. And when we say insulate, we mean electrically insulate. So we use a material that electricity cannot pass through, but will still allow magnetic permeability.
Hi, do you know what eddy current is? No, it's not some sort of ocean current that Nemo's father traveled to Australia with. Although the name comes from some swirling water currents. But I don't care about fluid dynamics. Eddy current is an electric current that's created in any conductor when there is changing magnetic fields around. And those currents make any conductor magnetic. What you have probably seen as an effect of eddy current is that throwing a magnet through a copper pipe slows the magnet down. This is paper though. I didn't bother buying a copper pipe just to add it to my collection of unused pipes here. I'm pretty sure it's easy to make one at home though. All I need is an aluminum foil I wrap around my paper pipe and tape it. Now my magnet drops through air at this rate and through the pipe. The exact same rate. Thanks for cheering me up. Well, I guess that's why we need to know how things work. And so in an attempt to fill your brains, this video is sponsored by Audible, because the more you read, the more you know. Except with Audible, you listen, you don't read, which is even better. You don't need to sit down and read a pictureless, boring book. Your hands are free, your eyes. Hi, do you know what the eddy current is? No, it's not.
All right, trying to skip the ad, didn't work. Yeah, so we'll talk about eddy currents, but basically, if anyone's wondering why the magnet didn't change, it's because aluminium is not magnetic, which is why you can't weld normally to it. Random factoid. Cool. So hysteresis. So this is a type of loss attributed to the constantly changing polarity of the magnetic field. When something becomes magnetized, its molecular makeup is rearranged. When the magnetic field is changing polarity 50 times a second, all of the atoms and molecules within the core are rearranged 50 times a second. As these atoms and molecules move, they create friction, which generates heat, and thus is not useful energy for us. Technically, when you think about it, a transformer does actually have moving parts, the electrons within the copper wires. Cool.
In this video, we're going to be going over how the hysteresis loop is formed. And what we mean by this hysteresis loop, it's a characteristic of, say, some sort of metal as to its retention of magnetism. So whether it retains magnetism or not. And so we're going to walk through this and hopefully you get a better understanding of exactly how this all kind of plays together. So what we have here is we have an x-axis and a y-axis. Our x-axis is labeled H. What that means is magnetizing force. Magnetizing force is the force needed to create flux lines. Our y-axis here, you notice, has the V, which is our flux lines. It's Tesla. So how many flux lines are being created? This little line here is our magnetizing curve. So what's happened here is, if you can see, is we increase our magnetizing force in, say, some sort of iron core or steel core, it could be any kind of metal, and you're going to see that the flux lines increase. So again, we're talking about a wire wrapped around a core. So we're basically creating an electromagnet. So this, as we increase our magnetizing force, then our flux lines increase until they get to a certain point. And that point is called our point of saturation, which means that no matter how much magnetizing force you can put on this, and keep increasing it, you can't put any more flux lines into that piece of metal. Because it gets to a point where it's like the toothpicks, when you're putting toothpicks into the little toothpick bottle, it gets to a point where it's all full. And so we hit saturation. So we're going to see what happens when we do that. We magnetize it. And then if we get rid of our magnetizing force, let's see what happens to this. As we get rid of our magnetizing force, so our magnetizing force goes back to zero, you'll notice that it retains some flux lines. This doesn't just drop out like that. What happens is the flux lines, there are some that retain or stay. So that might not be a good thing. You might want to get rid of those flux lines. So what we call this, though, is our point of retentivity or retention, which we're going to denote with that R. Now, if we want to get rid of this, what we have to do is put a magnetizing intensity on it in the opposite direction. So we gave it a positive magnetizing force, which created this magnetic line here, and hit saturation. We turned it off and went back here. We still have some retaining of magnetism here. So in order to get rid of it, we push it the other way, which could drop our current, or sorry, our flux lines down to zero. Now we call that coercive force, which we're going to denote with the C here. Now, if we somehow just kind of kept this magnetizing force going, it ends up creating another line like this, but an inverse line in this direction. So you see that it keeps going until it hits that saturation point again, but in the opposite direction. And then the same thing follows true. So it's going in the opposite direction, and we realize that we've left the magnetizing force on in the opposite direction. If we turn that off, what should happen, it should be the inverse of what happened up here. So we should see it drop back and retain some magnetism, but in the opposite direction. Which is exactly what has happened here. So we've retained some magnetic lines of force in the structure itself, but in the opposite direction of what they were there. So again, in order to get rid of this, we're going to have to coerce it into the other direction. Now, before we do that, we have to note that it is retained here as well. So we had retention up on the positive side, and we have retention on the bottom as well. Then we are going to coerce it back. So we put some more magnetic intensity on it in the opposite direction, and we can get rid of all those flux lines. We end up with a flux of 0 at this point too. And again, if we left the magnetizing force on in that direction, it would continue to go. So again, we had to coerce it. So this is our coercive force at this point here, which you can see with the big C. So again, if we were not paying attention and we left our magnetizing force on, what's going to happen is it's going to go in this direction again and still hit saturation and see what happens here. And we can see that it goes back and hits that point again of saturation, and the whole thing continues again. So what we end up with is what's called the hysteresis loop. Now, when we have cores that have a skinny hysteresis loop, meaning that when we let go of this and it goes back down close to 0, that is something that does not retain a lot of electromagnetism, which is something that would be good for, say, like a transformer or a coil, because you don't want it to retain that magnetism. Whereas if you're trying to create a big, huge electromagnet, you want to have it kind of come up top here. So what we talk about is how hysteresis loop for an electromagnet, something that you want to have retain its magnetism, is going to be relatively large or fat compared to if you have an iron core or something for a transformer or a relay or a coil, you want that to be skinny. So it's going to kind of, as soon as you get rid of the magnetic intensity, it's going to drop down closer to 0. So that's kind of the basic walkthrough of how a hysteresis loop is formed. And as always, if you have any more questions about this, we're going to be focusing a bit more on magnetism for a little bit, because you cannot have electricity without magnetism, and the two always go hand in hand. So I think it's important that we have a good grasp of magnetism.
Cool. So now that we've looked at the ion losses, including hysteresis and eddy currents, we can start talking about the copper losses. So because so they call copper losses as the windings of the transformer are traditionally made of copper. The resistance of both of the primary and secondary windings are relatively low. However, losses are proportional to the value of the current squared. With this in mind, copper losses can be exponentially high when load current is heavy. The energy that is expended due to the current flow is converted into heat, which to us is useless when considering a transformer's purpose, due to the fact that those losses are proportional to the current flowing in the windings. These losses are also known as variable losses. And to calculate these, we use the formula P equals I squared R. Now it says that they're useless and excess heat's not desirable, except for those who, among our society, sleep rough. I've heard from linesmen and that they routinely have to tell people to go away from the vents coming out of main transformer rooms because they are quite toasty in winter. Because the total losses must be calculated, we need to look at each side of the transformer. The formula can be modified to look like this. P equals IP squared times RP plus IS squared times RS. P being primary, S being secondary. When calculating losses, we must remember that copper losses vary at an exponentially proportional rate to the load current. This means that if the load current is 50% of full load, we must square the 50% minus, which equals 25%. So at 50% current draw, the power losses will be 25% that of full load. Cool, so measuring losses. So ion losses can be calculated by taking readings from the transformer with the method shown in the diagram. The test equipment is connected to the low voltage windings, regardless if it's the primary or secondary side of the transformer. The normal voltage is applied to the circuit, which induces the normal magnetic flux in the core. The secondary side is left open circuit so that the current from that side does not affect the test in the form of copper losses. The watt meter will read the power consumed by the transformer core by means of eddy currents and hysteresis. Yeah, you've got the watt meter there and in parallel with, well, it's kind of more in series with the supply, a voltmeter and an amp meter connected correctly. So that way we can measure the losses in power. Cool. So copper losses can be calculated by taking readings from the transformer with the method shown in the diagram. The test equipment is connected to the high voltage side of the transformer in a similar fashion to that of the iron loss test. A variable power supply is connected to the high voltage side and wound up to simulate full load current in the windings. With this full load current flowing in the high voltage winding and a short circuit on the low voltage winding, the transformer then simulates how it would operate in normal running conditions at full load. The copper losses are then measured by the watt meter. The voltmeter and ammeter are optional, however, if there is a discrepancy due to power factor, the results between the voltmeter, ammeter, and wattmeter will make this apparent. Cool. And then we can talk about efficiency. Cool. So the basic efficiency formula is percentage N equals P out divided by P in times 100. So basically the output power divided by the input power times 100, and that gives your efficiency percentage. So introducing losses, if we do not know the input power of the transformer, but know its rated output and its losses at the rated output, we can calculate its input power and its efficiency from there. The basic way to look at transformer losses is this: P in equals P out plus losses. And thus we can modify the basic efficiency calculation to include this losses formula. So therefore N equals P out over P out plus losses. Cool. So formula variations. So the formula finds this formula finds the losses as percentage and then subtracts them from the input at 100%, which is represented as the 1. So percentage efficiency equals 1 minus losses over output plus losses. The formula for efficiency as per the formula sheet allowed into the EWIB exam is as follows. Percentage N equals NS cosine theta over NS cosine theta plus N squared PCU plus PFE times 100. It's a lot to look at. So we'll break it down. Cool. So percentage N is the efficiency of the would it be output over in plus losses, not out? Are we talking about the loss? Are we talking about the losses as a percentage or the previous page? Talking about the previous page. So the PN equals P out plus losses. So we can figure out the efficiency by doing the P out and divided by the P out plus the losses, because we know that the input plus the losses equals the output. Sorry, yeah, the input minus the losses equals the output. So if we add the losses back into the output and then divide the output by that, we know that we're getting the efficiency. And then we can take the output and then divide it by the efficiency to get the input. Cool, all good. Yeah, just make sure, guys, if you're confused about anything at any point, please either turn your mic on and ask or type it into the chat, because I can see when stuff pops up and then go back and answer questions. Better you guys ask me these questions now than we get to the capstone and then you guys struggle, because the capstone will be online. It is computer-based. Basically, you log in. If you guys haven't been through an online test before, basically, or you should have for year one, but basically log in, do the test, and that's it. You're done. Yeah, there's no support really. I mean, I hear if you struggle with questions that don't quite make sense, but there's only so much I can do because I can't actually log in and see your test when we're doing it. Cool. So yeah, that big formula there, it's a lot to take in, so we'll break it down. So your percentage N is the efficiency of the transformer expressed as a percentage. So usually 20%, well, not that, probably more like 85%, 90%. Cool. So N is the load being applied to the transformer as a percentage. So a percentage of load. So say we're only applying 80% load, N would equal 0.8. Cool. S is the output power the transformer is supplying in VA, the apparent power. Cos theta, the power factor value of the transformer. And PCU is the power losses in copper. The N squared is the load value squared in order to get the proper copper losses dependent on the load. And then PFE, power losses it's not in copper, it's iron. Fe is iron. So Fe is the chemical symbol for, there's a periodic table lettering for iron. Cool, hold on, so we go back there. So cool, so the formula is the efficiency percentage is equivalent to the load percentage times the output power of the transformer times the power factor value of the transformer divided by that same value plus the load squared times the copper losses plus the iron losses times 100. Cool. Okay, let's try and work this into a calculation. So we want to find out the efficiency percentage of the calculation of a transformer. We know the load being applied to the transformer, so it's at 90% load. Okay, the output power of the transformer, or the apparent power, is 400 VA. I know it's not a lot. Okay, the power factor of the transformer is 0.95. Okay, the copper losses, so it should be in VA, is 5, and the iron losses 2. Okay. Have a go at putting that into the formula and see what you get. So when we write out a formula, so we know N is 90%, so percentage N equals 0.9 cosine of, actually, There's my eraser. You don't need to worry about the cosine because we already have it at times 0.95. Getting ahead of myself. So 0.9 times 400 times 0.95 over 0.9 times 400 times 0.95 times 0.9 squared plus times copper losses 5 plus 2. Cool. So we break that down into lines. So we know the top one is going to be the 0.9 times 400 times 0.95 gives 342 over 342 plus, so we do 0.9 squared times 5 equals 4.05 plus 2. So it's 342 over 348.05. Which gives us 0.9826, which times 100 to get our efficiency gives us 98.26%. Is that making sense to people? Because cosine of the angle is already power factor. So if we think back to our Pythagoras with our theory with our power factor, when you guys did AC theory, capacitance and inductive reactance, your power factor is cosine of the angle. So if your power factor, so your cosine theta has already been calculated because we've got a 0.95 power factor. So that's already cosine of the angle. So if you've been given the power factor, you don't need to worry about using the cosine. Okay. Did everyone else kind of follow along where I was going with that one? Okay, I will try and get the cool. So we'll give it a go at another one. So we have a transformer that has an efficiency. So we're trying to figure out the efficiency. So we know the load being applied to the transformer is 80%, which is 0.8. And the output of the transformer is 600 VA, and it has a power factor of 0.9. Cool. So we know this is the start of the calculation. So then we know we're dividing it by itself. So 0.8 times 600 times 0.9 power factor. And then we're adding in our copper losses. So it's the power factor. Okay. Nope. It's the load. So I screwed up on the first one. That's my bad. So it's actually plus 600 times the copper losses. So which we're going to put as 0.5. 0.05 plus the iron losses of 0.6. So we can simplify that top one to start with. So we go 0.8 times 600 times 0.9, and then we get yep, 432, yep, 432, and then we know we're going to be dividing that again by 432 plus, so 600 squared times 0.05. That's a lot. One 18432. Yeah, 600 squared is a lot. And even if we times it by 0.06, 0.05, my bad. So 600 squared is 360,000 times 0.05 gives 18,000. And then plus 0.6. So yeah, that'll be 432 divided by 1842.0.6. So it's going to be very inefficient. So 432 divided by 18432.6. So it's 0.023, which when times by 100 gives us 2.34%. Very inefficient. All right. We'll carry on with the presentation, and then we'll come back and do some more calculations. So the 0.6 is the iron losses. Cool. So we've studied the regulation. So we've looked at the past at when current flows in a circuit, a volt drop occurs across the circuit. So one of Kirchhoff's law states when one or more loads are connected in series, the sum of the potential differences across the loads are equal to the supply voltage. When we think about a circuit comprised of a supply via a transformer and a load, we can see that the two components are in series with each other. Like everything, the windings of the transformer have resistance, so therefore two loads in series with each other will see a volt drop across each one. And some of these will total the supply. This means that when a transformer is supplying a circuit, a certain amount of voltage will be dropped across its secondary windings, leaving the rest to be fed across the load. If the load becomes too high, the current draw from the secondary winding will cause such a volt drop across itself that the supply voltage of the rest of the circuit falls below acceptable levels. The difference between the voltage measured across the terminals of the winding when there is no load present and when there is full load present is called the regulation of the transformer. This regulation is expressed as a percentage and can be calculated by using the following formula: VNL minus VFL divided by VNL times 100. So voltage no load minus voltage full load divided by voltage no load times 100. So, just realized there's a bunch of writing on the board that can be rubbed off now. Cool. So if the regulation becomes too high and voltage to the load drops too much when fully loaded, the transformer can be adjusted so that the level can be brought back up. This is done with the tap changer on the high voltage side. This will cause no load voltage to be higher than usual to compensate for when load is applied. However, transformers are constructed so that they can be adjusted up to an acceptable value that isn't too high, but manage the dip in voltage during peak load times. So there are some regulatory requirements. So the electrical safety regulations, or ESR, stipulate the levels of voltage that must be supplied to works and installations. They state ESR 28.1, the supply of electricity to installations operating at a voltage of 200 volts AC or more must not, but not exceeding 250 volts AC, calculated or measured at the point of supply, must be at standard low voltage and, except for momentary fluctuations, must be kept within 6% of that voltage. This means that for an installation operating at standard low voltage, 230 volts, the transformer must be able to supply a voltage within 6% difference of that value. So if we look at the following calculations, so V regulation equals 230 times 0.6, so 13.8 volts. So the voltage allowed to be, except for momentary fluctuations, 13.8 volts greater or less than the standard low voltage of 230 volts. This is V min, V max, 230 plus or minus 13.8, which is 216.2 volts or 234.8 V max, which is strange because I swear I have measured 240 volts coming out of socket outlets before, but maybe that doesn't count because it's not the point of supply. So point of supply being your fuse or pillar box. Cool. So potential hazards. So as with all electrical work, there's a degree of danger associated with working on transformers. Working on transformers, particularly large supply transformers, must be done with the utmost care and is often done by specialized skilled workers, so linesmen and transformer technicians. When working on large transformers, they either come with a high voltage risk or high current risk. When working on the 230, 400 volt side of a supply transformer, there can be the potential for enormous fault current, as if there is a short across the transformer terminals. The only opposition to current flow is the impedance of the windings themselves. A transformer with a 5% impedance and a rated current of 1,000 amps on the secondary terminals can see a 20,000 amp flow in the event of a fault, which is a tremendous amount of energy released in a short time. With this in mind, the hazards that can be associated with working on transformer as follows: electric shock, fire, explosion, arc flash, scalding by hot oil, damage to equipment and property. So with all of these hazards, we must take extreme caution when working with transformers. Some means of precaution can be performing a full risk assessment and job analysis prior to commencing work, the paperwork and risk assessments, Familiarize yourself with the equipment you're going to be working on. Read all the safety documentation. Make sure you know exactly what you're going to be working on and where it's located. Follow a documented switching on and or isolation procedure. Adhere to minimum approach distances. Follow appropriate PPE. This might be high voltage gloves, low flame overalls, face shield, extra layers of insulation, or the bomb suit as pictured there, as the guys like to call it. Always test for voltage. Follow the manufacturer's instruction. Maintain situational awareness. Watch for things out of the ordinary, like strange noises, movements, or smells. If it makes a weird buzzing noise, stop, drop, and roll. Keep track of all tools and equipment used in the transformer. Never work alone. Never become complacent. So always test for voltage and make sure the voltage testers you are using are correctly rated. If you're working on a 11,000 volt transformer, no point using equipment that's only rated for low voltage. Cool, so legislation. So medical areas and equipment. So medical areas have very strict regulatory requirements as the risks present are a lot higher. Skin is a good insulator, so areas in where skin can be compromised, such as surgeries, patient areas and the like, higher levels of safety must be enforced. Some of these degrees of safety can involve transformers. Other times, high voltages are required in medical areas such as X-ray machines. As AS/NZS 3000 has a section specific to special installations, Section 7. In this section, it makes reference to additional standards that must be adhered to due to their special nature. Clause 7.8.2.2 refers to electromedical treatment areas, where it cites AS/NZS 3003 as an additional standard that must be adhered to. So one thing with that is that surgical areas require isolation transformers for the equipment that's being used above or near the operating table. So one job I did most recently was Wakefield Hospital, working on the 7 new operating theatres there. So all 7 operating theatres required isolating transformers mounted in the corridor outside, and they were for the power points, lights, and all the equipment that is being used around and above the surgical table. So that way those pieces of equipment are isolated from earth. So if the patient is the surgeon is touching the light or the socket outlet and the patient at the same time, there's no chance of a return path being created through the floor or any exposed metalwork because there is no connection to earth. That makes sense. So circuits that operate at extra low voltage can come in many different shapes, forms, and applications, from lighting to communications or control equipment. All extra low voltage circuits and installations are regulated as AS/NZS 3000, in particular section 7.5. Cool. High voltage discharge lamps, not too common nowadays because we have high powered LEDs. So light fittings that emit light by energizing a gas vapor within them often require a high voltage to ignite the gas in order for it to work properly. These fittings require a transformer to step the voltage up from the installation's voltage level to the required level for the fitting. Section 7 and 3000 refers to this particular installation. 7.8.2.6 cites AS/NZS 3832 as an additional standard that must be adhered to. The auto transformers. So there's a lot of legal stuff here. Section 4.14 and 3000 refers to the general requirement of transformers other than the exception stated in 1.14.1. In particular, a part of section 4.14 refers to restrictions for auto transformers. Clause 4.14.4 states that auto transformers shall not be used to supply electrical equipment, including circuit wiring, having a voltage rating of less than the highest input or output voltage of the auto transformer. In other words, they cannot be used as step-down transformers if the equipment it is supplying is not rated for the full supply voltage, because if there is a fault with the transformer, the full supply voltage can be applied to the equipment, creating more of a risk. So you can't use it to supply 12-volt equipment if that 12-volt equipment is not rated for 230 volts, because if there's a fault and 230 volts is applied to that equipment, it will more than likely melt and cause a fire risk. Electric toys. So the international standard, so the IEC 62115, refers to the requirements regarding the supply of electricity to equipment used as toys for children. Part of the standard includes the requirements regarding the supply of electricity to the toys, such as voltage levels and method of supply. As toys must be at extra low voltage levels, transformers must be utilized to reduce the supply to a lower level. IEC 62115 stipulates the types of transformers that can be used. Note, toys for children, not toys for adults. Toys for adults, you can do whatever you want. Cool. Turn that off. So we'll go through some of those questions, through some examples. I have some here. Cool. So first we'll start off with, come on. Cool. So we'll start off with the usual for another one. Cool. So we know that NP over NS equals VP over VS. Cool. So we know that the number of turns in the secondary, so is 1, and we know that the number of turns on the primary are for 7.8 over 1. It's a ratio. And then we know that the voltage primary is 1000. Then we need to figure out the voltage secondary. So to do this, we can rearrange the formula. So voltage secondary equals NS times VP over NP. So whenever we do this formula, we know that if we need the voltage secondary, we multiply top and bottom. So we multiply and then we divide it by the other. So the number of secondary turns times the voltage primary times the number of, divided by the number of primary turns, which gives us 1 times 1000 divided by 47.8, which gives us 230 volts. Cool, sorry, I got that wrong. Yeah, voltage primary 1000. Got them around the wrong way. Or my workbook that I have open is all kinds of back to front. Cool. So you guys give it a go. So we know VP over VS equals NP over NS. So we have a 11 kV transformer with down to 230, And we know we do not know the number of primary turns, but we do know that it has an equivalent of 3 turns on the secondary. So NP equals so we need to know the NP. So we're going to take the voltage primary and we're going to multiply it by the number of secondary turns. And then we're going to divide that by the voltage secondary. Yeah, we know we're going to do 11,000 times 3 divided by 230. And we can simplify that down to 33,000 divided by 230, which, yeah, as Ollie correctly said, is 143 point, well, it's 47826, etc. But we simplify it to 143.482 dP voltage. Current primary. Are you talking about the power? Voltage turns current formula. Are you talking about the efficiency one? Ah. Yes. Okay, so yeah, when we're talking about current, so if we're talking about numbers, primary is equivalent to voltage primary over like this. Then it's the opposite for current. So we're looking at IS over IP. So because with transformers, current and voltage are inversely proportional, so the more voltage, the more current. Okay, so we can do something similar. So cool. So we know the voltage primary. So VP equals, let's go with 2 kV. VS equals 400. And we know that I primary is 1.5 amps. Cool. So figure out the secondary current. So we write out the formula for this one. So voltage primary is 2000 over 400, which equals, so I primary is 0.5, and then we need to find I secondary. So for this, it's going to be 2000 times 1.5 divided by 400. Cool, which gives us a total of 7.5 amps. That makes sense to everyone, or so basically all we've got to remember is that with this formula, current and voltage are inversely proportional, because the more voltage you pull on a more current you pull on a transformer, the voltage dips. So yeah, whenever we're working out stuff like this, we need to remember that. Cool. So I'll leave the formula there, and then we'll go with voltage primary of 230, voltage secondary of 24 volts, and an I primary of 0.02 amps. So IS equals, I'll leave that for you guys to figure out. Cool. I'll wait till you more of you guys have a guess, and then I'll go through it. But then after you've done the I supply, have a go at power in the primary, and then power in the secondary. This is assuming no losses though. Cool. So to work this out is basically IS equals. Cool. So IS equals. So voltage primary or 230 times current primary, 0.02 amps divided by 24 volt, which gives 0.19. Technically, that's where it should be. If we're doing 2 decimal places, that would be there. If you guys were doing 1.3 decimal places, because it ends up to 1.9, so 0.1916, you would round it to 192. But yeah, 2 decimal places, 9 amps. So we'll then put our supply in at 0.19 I secondary amps, and then power, it should be the same. So primary should be 230 times 0.02, and then power secondary should be 24 times 0.19. So if anything, it would be rounding errors. So this should give you 4.6. And then 24 times 0.19 gives 4.56 within spitting distance, so within 0.04. So yeah, there's rounding errors, but really it should be 4.6 on both sides because power is just V times I. So it should be the same on both sides. It didn't work out this way. Cool. So now we'll work on efficiency. Cool. So percentage N equals P out over P in times 100. Cool. So if we've got a $240 VA transformer, but we're only using 215 watts on the other side, what is our efficiency? So simple, we just go this times 100. $240 divided by 215. No, other way around. Flip them. So it equals 215 divided by 240 times 100, which equals 0.8958, etc., times 100, which equals 89.58%. Cool. So now that we've done one, cool. So we have a 6 kVA transformer, but we're only getting 5.2 kilowatts on the output. What is the percentage of the efficiency? Yeah, because your transformer is rated in VA, volt amps, but your load is in watts or kilowatts. So yeah. Yeah, so you always have transformers rated in VA, and then the output is in wattage. Because a transformer, no matter how efficient, is never going to put out exactly as much as put in. Cool. Yeah. So basically, it's P out divided by P in. So we take 5.2 kilowatts or 5,200 watts and divide that by 6 kVA or 6,000 VA, and then we times that by 100, which gives us 86.67% to 2 decimal places. Cool. And then we can work out our losses because we know that P in equals P out plus losses. So therefore, losses equals P in minus P out. You'll be given a physical sheet. You'll be given one physical sheet. Yeah, for the capstone, it'll be digital. It'll be a digital formula sheet. For the EWOB exam, you should be given a paper sheet. So now that we can work out our losses, so 6,000 minus, 5,200, we know that we're losing 800 E. Basically, it's being used as heat and copper losses in eddy current, so we can call it watts. We're losing 800 watts within the windings. You could say VA as well, but yeah, we're losing 800 watts inside the windings, which is a lot. So yeah, a formula to be given in your EWRB exam looks a lot like the second formula, the last formula that we're looking at with your percentage N. I'm just trying to find the formula sheet for the EWRB exam now. Try the last formula. So we know that we have, so we're looking at the efficiency formula sheet is the EWRB exam. Cool. So we're trying to find the percentage N. So we know the load being applied to the transformer as a percentage. So we're going to say at 0, it's 98% loaded. We're going to say that the output power of the transformer it's supplying in VA, the apparent power is 230 VA. The power factor is 0.9. The copper losses are so PCU 0.003 and the iron losses PFE 0.03. That's the power factor. The formula we were looking at before, so percentage N equals, yeah, so it's NS cosine theta divided by NS cosine theta plus N squared PCU plus PFE. Yeah, so this is the only, other than that N1 over N2 equals V1 over V2 equals I2 over I1, this is the only formula you're going to be given for the EWRB exam. And P out over Pn equals times 100 equals percentage. And your regulation. So you get a few of these formulas that we're looking at. Cool. So let's write it out. Cool. So NS cool. So I know my N is the load being applied times as a percentage. So I know it's 98%. So 0.98 times 230 times the power factor of 0.9, which then gets divided by the same 0.98 times 230 times 0.9 plus N squared, so 230 squared times the the copper losses, which is 0.003 plus 0.03 for the iron losses. Cool. Cool, that's a big number. So it works out to 207 over 207 plus 230 squared times 0.003 plus 158.7 plus 0.03. So that gives us 207 divided by 365.73. So 207 divided by gives us 0.5659 times 100 gives us 56 with rounding 6%. So within 0.5%. All depends on the order you do things. I tend to do things, break things up into chunks, do the calculations bit by bit. So that way it's less likely that I've accidentally done something wrong. But, you know, if you get the question wrong in the capstone and you want to challenge it, we can moderate and go through and see how close you got and be like, okay, 0.5%, that's just a rounding error in some of his calculations. I think we can let that go, but that'll be up to whoever's moderating it. No, there's no working stages in the capstone or any of the theory exams anymore because it's all digital. Basically, if there might only be one value that they want, but sometimes you'll have to enter multiple values along the way. Yeah, so we're getting towards the point where there's more maths. So next week, we'll be moving into three-phase transformers and starting to be doing three-phase calculations. Just gonna stop recording. Cool, so that's